Hello friends, welcome to engineering tutorial. So we'll continue our discussion on signed binary numbers. Previously we discussed 1's complement arithmetic where we performed addition and subtraction operations using 1's complement. Here we will be doing 2's complement arithmetic. Okay, and it is very important because most of the arithmetic digital circuits, combinational circuits, they employ 2's complement arithmetic. So in a similar way we'll be performing different arithmetic operations using 2's complement arithmetic. So starting with the most basic one, which is the case 1, when both numbers are positive. Okay, so let us perform the arithmetic operation. Let's say 19 plus 27. Okay, now first we have to represent 19 and 27 in terms of their binary equivalents. So 8-bit representation will be using. So plus 7, plus 6, 5, 4, 3, 2, 1 and 2 to the power 0. Now we have to split these individual numbers with respect to powers of 2 into the individual components. For example, we can split 19 as 16 plus 2 plus 1. 16 plus 2, 18 plus 1. So this is 2 to the power 4, this is 2 to the power 1, and this is 2 to the power 0. So these respective weight positions, it will have 1's. So 2 to the power 2 to the power 4, 2 to the power 1 and 2 to the power 0. And the remaining positions we have 0 bits. Similarly, this is for plus 19. Similarly, 27 can be split as 24 plus 3. Okay, 24 can be split as 16 plus 8. 3 can be split as 2 plus 1. So we have 2 to the power 4, 2 to the power 3, 2 to the power 1, 2 to the power 0. Now if this splitting thing is difficult for you, then you can use the repeated division or LCM method and the remainder method to convert any decimal number into binary. But this process of splitting into individual powers of 2, that is easy. I mean, when you practice it on enough decimal numbers, you get acquainted with it. So we have plus 27, this is plus 19 and plus 27, that because they're positive numbers. So it is 2 to the power 4, 1, 2 to the power 3 is 1, 2 to the power 1 is 1, 2 to the power 0 is 1. And the remaining bit positions are 0. Okay, so now when we add both of these, we get the result. Okay, 1 plus 1 is 0 with a carry of 1. 1 plus 1, 0 with a carry of 1. That 0 added with this previous carry 1, it becomes 1. 1 plus 0 plus 0, that is 1, 1 plus 0 plus 1, that is 1, 1 plus 1 is 0 with a carry of 1. This comes down here, it becomes 1, and then 0 and 0. So we have 00, 10, 1110. This is the result. Now we have to check whether it is the right answer or not. Now in decimal form, plus 19 plus 27, that is 46. Now let us convert it into decimal form to see whether it is the correct answer or not. So this is the decimal value here is equal to 1 into 2 to the power 5 plus 1 into 2 to the power 3 plus 1 into 2 to the power 2 plus 1 into 2 to the power 1 equal to 32 plus 8 plus 4 plus 2 is equal to 46. Okay, this. Now here the important thing, this is called as the sign bit, this MSB bit. It is 0, so it means it will obviously be a positive number. So that's why I went directly with this. No need to attach any negative weight to the sign bit because it is 0. Okay, so this is the 2s complement operation on addition of both numbers when they are positive. Now in 2s complement representation, the positive numbers are represented in the same way as in sign magnitude and 1s complement. It is the same. Okay, we have to put this 0 in the MSB bit, the sign bit, and the remaining bits they represent the magnitude, and we have done the same thing here. When it comes to negative numbers, the situation changes, which we'll see in the upcoming questions. So this is the first operation.